Something is passing through your hand right now, not touching it. Passing through it, the way a thought passes through a room that isn't paying attention. It came from about 93 million miles away, and it did not slow down to do this, and in about 1 second, roughly 100 trillion more of them will have gone through the same hand, and you will not have felt a single one. That number is not an exaggeration for effect. It is closer to an undercount. Nobody warns you about this before you learn it. You go your whole life assuming your body's a wall, a boundary, skin, then not skin, and then someone hands you the actual number, and the wall stops behaving like a wall. The thing passing through is called a neutrino, and it has almost no mass, no charge, and essentially no interest in you. It was born, most of these particular ones, in the core of the sun, in a fusion reaction that also made light, real photon light, but the light stayed behind, trapped, bounced around in there for longer than you'd believe. The neutrino just left, walked straight out through 800,000 kilometers of solar plasma, as if the plasma were a suggestion rather than a barrier, then out across the vacuum, then through the wall of your house, if you're inside one, and through you, and out the other side, and it did all of that in about 8 minutes flat. You are, structurally speaking, mostly empty space held together by forces that are very good at stopping some things and not remotely interested in stopping this. A neutrino could pass through a solid wall of lead a light year thick, and there's a real, calculable chance it would come out the other side having touched nothing. Not unlikely to be stopped. Actually likely to go straight through, untouched, unbothered, same particle it was when it left the sun. Here is the part that sits wrong in a good way. Every single person who has ever stood outside on a clear day has been, without exception, a kind of colander for the sun, full of holes it never uses. And nobody tells you this at the time. You just stand there feeling solid, feeling like a person, and this entire invisible traffic is going through your chest at a rate that would be, if it were anything else, anything with mass or charge or manners, instantly lethal. It isn't lethal. That's the strange part underneath the strange part. The reason it isn't lethal is the same reason it's almost impossible to detect. It does essentially nothing when it interacts with matter, and it almost never interacts with matter at all. The detectors built to catch these things are enormous on purpose. Tanks of water the size of buildings buried under mountains, in old mines, shielded from every other kind of particle that might confuse the signal, and even then, out of the unthinkable number passing through the tank every second, only a handful get caught doing anything. A handful. Out of trillions. The rest just go on, indifferent, already leaving the planet, already halfway to wherever a straight line eventually takes something that never stops. There's a particular kind of vertigo in learning that your own body has been transparent this whole time to something you can't feel, can't see, can't stop, and never ask permission to pass through. It changes the definition of alone in a room. You are not. And here's where it gets quieter, not louder. If you go outside at night, most of what's overhead is not the sun. It's other stars doing the same thing, at distances that make the sun's 8 minutes look like nothing at all. Some of that light left before there were people to look up at it, and travelling alongside that light, ahead of it in some cases, behind it in others, is the same kind of particle, headed the same direction, through the same kind of nothing, having gone through God knows how many bodies before yours, on the way to somewhere it will never notice arriving. By the time you notice a star, the noticing is already late, not late in the way you're late for something, not a delay you could have closed by moving faster. Late in a way that cannot be fixed by anyone, ever, because the thing you're looking at finished happening before the looking started. This is true of every star you have ever pointed at. Every single one. The star up there right now, the one your eye landed on without meaning to, is not there right now. It was there. Whatever it is doing at this exact moment, you will not find out for years, and depending on which star it is, you might not find out for longer than your own life is going to last. People don't usually sit with this. It gets mentioned once, in a documentary or a classroom, said quickly, and moved past, the way you'd mention that a plane is basically a controlled fall. Technically true, immediately abandoned, because dwelling on it would change how the rest of the flight felt. Light has a speed. It is fast, faster than anything you will ever personally encounter, and it is also not infinite, and that second fact is the one that does all the damage once it lands. Here's the plain arithmetic of it, because the arithmetic is the whole horror and the whole beauty at once. Light moves at about 300,000 kilometers a second. The nearest star other than the Sun, Proxima Centauri, sits about 4.2 light-years away, which means the light reaching a telescope tonight left that star 4.2 years ago and has been travelling, uninterrupted, ever since. Nothing happened to it in transit. No aging, no slowing down, no forgetting. It just kept going. The same information the whole way, arriving now the way it would have arrived at any point during those 4 years. Identical, because light doesn't experience the trip the way anything with mass does. From its own perspective, and this part is strange enough that professional physicists still choose their words carefully around it. No time passed at all. Move outward, and the numbers stop being numbers and start being something closer to a small crisis. Betelgeuse, the reddish shoulder of Orion, sits somewhere around 500 to 700 light-years off, the distance still debated because it is hard to measure precisely, and either way the light hitting your eye left before the printing press existed, before a huge portion of what you'd call recorded history had happened yet. Betelgeuse is a red supergiant near the end of its life, and it could in principle have already ended. Gone. Collapsed. Exploded, finished, sometime in the last several centuries, and the sky would give no indication of this until the light of that ending finally crosses the distance and arrives. You will be looking at a star that isn't a star anymore, glowing exactly as if nothing had happened, because as far as the information reaching you is concerned, nothing has. Sit with that for a second longer than feels natural. Somewhere out there, right now, is a genuine, unresolved possibility. The star is gone. Not might be gone in some vague philosophical sense. Actually gone, in a way that is either already true or not true, and there is no way for anyone on Earth to know which, because the only messenger that could tell you is still en route. The universe is, in this very specific and very literal way, keeping a secret from you that it isn't trying to keep. It's not hiding anything. It just hasn't arrived yet. Astronomers have a term for the delay. Look back time. It sounds administrative, filed away in a textbook, and then you actually use it and it stops sounding administrative at all. Every telescope pointed at the sky is, in the most literal sense available to any instrument built by humans, a time machine, except it only runs in one direction and it can only show you the past, never anything closer to now, and there is no version of any telescope, present or future, that fixes this. It's not a limitation of current equipment. It is the actual condition of watching anything from a distance in a universe where information has to travel to reach you. Go far enough, and the delay stops being personal and starts being historical, then stops being historical and starts being something closer to geological. The Andromeda Galaxy sits about 2.5 million years away, and the light arriving from it tonight left before modern humans existed as a species, before agriculture, before fire was reliably kept, before most of what would eventually become a human story had happened even once. Point a telescope at the deepest surveys ever taken, and some of that light has been travelling for over 13 billion years, meaning it left when the universe itself was young enough that stars as we understand them were still a fairly new invention. That light is arriving now. Tonight. Landing on a detector that didn't exist 100 years ago, carrying a report from a universe that, by the time the report shows up, no longer looks anything like what it's describing. None of this is a trick of the mind, a metaphor stretched past its usefulness. This is what seeing actually is, once you follow it all the way down. Vision is not instant. It never was, not even across a room. The light bouncing off a person's face and reaching your eye takes a small but non-zero amount of time, a few nanoseconds, too brief for anyone to register as a delay. Stretch the distance out past a room, past a city, past a planet, past a solar system, past a galaxy, past a universe, a city, past a planet, past a solar system, and the delay stops being too brief to notice and starts being the entire subject. You could go your whole life without needing this fact for anything, and that's part of what makes it sit strangely once you actually have it. It doesn't change how you drive or what you eat or who you call back. It just changes what you're doing, quietly, every single time you look up on a clear night without thinking about it. You are not observing the sky. You are receiving a delivery. Some of it fast, some of it centuries old, some of it old enough that old starts to lose its meaning. All of it arriving in the same instant, stacked on top of each other, none of it simultaneous with anything else in the frame, and none of it simultaneous with you. There's a particular kind of stillness in realizing that the sky has never once shown you the present. Not tonight. Not any night. Not once in the entire history of anyone looking up. Start far enough back and the sun is just a shape. A bright coin held at arm's length, warm in a way you stopped questioning as a child, up there doing whatever it is the sun does, which you have never really had to specify. Most people could not tell you what is actually happening inside it, and that's fine. Most people don't need to. But go closer, not physically. Nothing gets closer to the sun and survives to describe it. But in imagination, in the place where you're allowed to shrink yourself down and walk into things that would otherwise kill you instantly. Go down through the outer layers, past the visible surface, past the boiling orange skin everyone recognizes from photographs, and keep going, because none of that is where the actual event is happening. The event is happening at the center. A region about a quarter of the sun's radius, where the pressure is roughly 250 billion times what you're feeling right now sitting wherever you're sitting, and the temperature sits around 15 million degrees, numbers so far outside anything a body could survive that they stop feeling like numbers and start feeling like a kind of myth. And in that pressure, in that heat, hydrogen nuclei are being forced together against their own repulsion, fusing into helium, and in that fusion something is being made. Light. actual photons, born the same way the ones on your skin were born, at the exact centre of the star. You'd think, reasonably, that a photon born at the centre of the sun would be nearly to the surface by the time you finished reading this sentence. Light is fast. You already know that. But this is where it stops behaving the way you'd expect, and I have to be honest. This is the part where even people who study this for a living start hedging their language a little, because the numbers involved don't fully resolve into agreement. The core of the sun is not empty. It is almost unimaginably dense, a plasma so thick with charged particles that a newborn photon cannot simply leave. It travels a tiny distance, a fraction of a centimetre, sometimes less, before it is absorbed by a particle and re-emitted in a direction that has nothing to do with where it was originally headed. Then it happens again, and again, not gently, not occasionally, constantly, at a rate that is difficult to even describe as a rate, because rate implies progress, and what's happening here barely qualifies. Picture someone trying to leave a room, except every single step in every direction. Someone gently spins them around before they can take the next one. Not violently, not maliciously, just constant, disorienting, directionless redirection. Now make the room several 100,000 kilometers across, and make the spinning happen roughly 10,000 trillion times a second, and you start to get something close to what's happening to a single photon somewhere below your feet's equivalent depth in the sun, right now, this second, and every second before this one, going back roughly 4.5 billion years. The estimates for how long this takes, for a photon to random walk its way from the core out to the surface, vary. That's not evasive, that's just the honest state of the science. Some estimates put it at tens of thousands of years. Others, depending on the model of the sun's interior used, put it well over 100,000. I've seen serious people cite very different numbers with real confidence, and I don't think that's a failure of the science, so much as a sign of how genuinely hard it is to model a journey made of that many collisions in a place no instrument will ever be able to reach directly to check. Here's where it slows down, because it deserves to. Sit with the shape of it for a second. Somewhere below the visible surface of the sun, at this exact moment, there are photons that began their trip outward before humans had agriculture, before there were cities, before most of what you'd call civilization had happened even once. They are still in there, still being absorbed, still being re-emitted, still going nowhere in particular, patiently, without any sense that time is passing, because photons don't experience duration the way you do. That part isn't uncertain. That part is settled physics. And so from the photon's own vantage point, if it had one, none of this delay would register as a delay at all. Only from the outside does it look like waiting. Then, eventually, near enough to the surface that the plasma thins out and the density drops, a photon finally escapes the last collision that was going to redirect it. And from there the trip is fast again, ordinary again, 8 minutes to Earth like everything else. It crosses the vacuum in the time it takes to make a cup of tea. That final leg, the one everyone learns about, the one that gets taught, is the shortest and simplest part of a journey that mostly happened in the dark, going nowhere, for longer than most of human history has lasted. So when the light hits your face on an ordinary afternoon, and it feels immediate, because it does, it feels like the most instant thing in your entire experience of the world. Most of that photon's actual life was already over by then. The interesting part, the slow part, the part that took tens of thousands of years or more, happened somewhere you will never see, in a place too dense and too violent for anything to survive checking, and by the time the photon reaches you, all that's left is the easy part, the part that looks instantaneous because compared to everything that came before it, it basically is. I don't know that anyone has ever fully sat with that asymmetry. Most of a sunbeam's story is delay. Almost none of it is arrival. Something is about to sweep past you. Not light exactly. A beam, aimed at nothing in particular, moving in a circle far too fast to be a coincidence. It hasn't reached you yet. It will in a fraction of a second, and then it will be gone again, and then it will come back. This has been happening for longer than anyone alive has been alive. Zoom out first, wide as it gets. A galaxy, spinning slowly, unremarkable from a distance, one of several 100 billion doing roughly the same thing across the observable universe. Somewhere inside it, a star died a long time ago, not gently. The core collapsed inward under its own weight until protons and electrons were crushed together into something new, something that had never existed in that particular arrangement before. Neutrons, packed so tightly that a teaspoon of the resulting material would weigh, on Earth, something in the range of 1 billion tons. Zoom in. The dead star that's left behind is called a neutron star, and it is small, absurdly small for what it used to be. A city-sized object, maybe 20 kilometers across, holding more mass than the Sun. When the original star collapsed, it kept its spin. Angular momentum doesn't just disappear, and because all that mass compressed into a much smaller radius, the spin sped up. Dramatically. The way a skater pulls their arms in and spins faster, except the skater here went from something the size of a solar system down to something the size of a city, and the resulting spin can reach hundreds of rotations per second. Zoom in further. Some of these spinning remnants have powerful magnetic fields, and the field is very rarely aligned with the spin axis. It's off, tilted, the way a flashlight taped crookedly to a spinning chair would throw its beam in a circle instead of straight ahead. Along the magnetic poles, charged particles get accelerated and emit a narrow beam of radiation. That beam sweeps around with the star's rotation, around and around, hundreds of times a second in the fastest cases. Zoom in past that to the smallest scale this idea has. A single pulse of radio waves, leaving the magnetic pole, travelling outward in a beam only a few degrees wide, indifferent to whether anything is in its path. Now zoom back out, all the way, and here's the part that reorganizes everything you just pictured. We only know these objects exist as pulsars, a name built from pulsating star. Though they don't pulsate at all, they just spin, because Earth happens to sit inside the narrow path of that beam. The object was always there, always spinning, always emitting. What changed was not the star. What changed was geometry. Us, standing in the one place out of an entire sphere where the beam happens to cross. Move the beam 5 degrees in any direction and the same object exists, unchanged, spinning at the same rate, still radiating exactly the same energy, and no telescope on Earth would ever detect it. It would sit there in every catalogue as nothing, not because it's fainter or older or less interesting, because the lighthouse isn't for anyone, and most of the time it isn't for us either. There are almost certainly more of these than we've found. Far more. Every pulsar catalogued is a pulsar whose beam happened to sweep this direction. The ones whose beams miss Earth by even a small margin are functionally invisible. Not hidden, not disguised, just aimed somewhere else, forever, doing the exact same physics as their detected cousins and never once being seen doing it. The first one was discovered in 1967 by a graduate student who almost dismissed the signal as interference from a piece of equipment. She didn't. The signal repeated precisely, every 1.337 seconds, regular enough that for a short while, the joke around the observatory was that it might be artificial. It wasn't. It was a star, 20 kilometers wide, spinning in the dark, aiming a beam of radiation at a very specific and very small patch of sky that happened, by no design at all, to include a radio telescope in England, objects that glow in a colour. You can't open your eyes to. It is already glowing by the time anyone thinks to look for it. Has been for a very long time, in fact, quietly, in a part of the spectrum that nobody's eyes were ever built to register, radiating away heat left over from a birth that happened before it had any real chance of becoming what it was supposed to become. I've come back to this one a few times over the years, and it still catches me a little differently each time, which is unusual, because most facts wear down the second or third time you sit with them. Start with what almost happened. A cloud of gas and dust, mostly hydrogen, begins to collapse under its own gravity, the way every star begins, pulled inward by its own weight until the centre gets hot enough and dense enough for fusion to ignite. That's the recipe. That's the whole recipe, more or less, for every star burning in the sky tonight. But the recipe has a minimum. There's a threshold mass below which the collapsing core never gets hot enough, never gets dense enough for hydrogen fusion to properly catch. Somewhere around 80 times the mass of Jupiter is roughly where that line sits. Below it, the object collapses, heats up briefly and dramatically, and then just doesn't. The fire that was supposed to start doesn't start. Not properly. Not in the way that keeps a star burning for billions of years. What's left is called a brown dwarf, which is a slightly unfair name because most of them aren't brown. Not in any sense a human eye could confirm, since most of them aren't emitting much of anything a human eye could catch in the first place. Here's where it sits, layered under everything already said. A brown dwarf does undergo a brief period of fusion, deuterium fusion, a lighter and much less demanding reaction than the hydrogen fusion that powers real stars, and that gives it an early phase of actual visible glow, dim and reddish, fading fast. But that phase ends quickly on stellar timescales, within tens of millions of years, sometimes less. After that there's no more fire. What's left is heat. Just heat, generated by the last of the gravitational collapse and slowly leaking away into space, the way a coal keeps glowing orange long after somebody stopped feeding the fire, cooling for millions, sometimes billions of years, radiating that leftover warmth outward mostly as infrared. Infrared is where this gets strange, and I don't think I ever fully got used to it. Your eyes are tuned to a narrow band of the electromagnetic spectrum, wavelengths roughly between 380 and 700 nanometers, and that band was not chosen at random. It corresponds more or less to where sunlight peaks in intensity after passing through Earth's atmosphere. Evolution built your retinas around the light that was actually available and actually useful. Infrared light sits just past the red end of that range, at wavelengths your retina physically cannot convert into a signal your brain can use. Not too faint, not too rare, just the wrong shape of light for the equipment you were issued, so a brown dwarf can be, in a very real physical sense, glowing, emitting real energy, real photons, measurable by the right instrument from a meaningful distance away. And if you stood in front of one, which you couldn't, not safely, but set that aside, your eyes would report back almost nothing. A faint reddish smear, maybe, from the last dying edge of visible light bleeding off the object's total output, and then darkness, as far as you're concerned, even while the thing in front of you is radiating away heat by the truckload in a colour your biology simply never learned to read. This is the part that took me longest to actually sit with rather than just repeat. It is entirely possible to be standing in front of something that is unmistakably glowing and to see nothing. And to be completely correct, in your own limited terms, when you report that you saw nothing, the object isn't hiding. It isn't dim in any way that matters to the physics. It's just glowing in a language your eyes were never taught. There's a version of this that shows up much closer to home, and it's the one that eventually made the whole idea feel less abstract to me. Your own body is doing something similar right now. Every warm object emits electromagnetic radiation as a function of its temperature. This is basic thermal physics, true of a brown dwarf and true of a human hand. And a human body sitting at around 37 degrees Celsius radiates most strongly in the infrared at wavelengths your own eyes cannot register even slightly. You are, in this very narrow and very literal sense, glowing right now, continuously, and have been your entire life, and you have never once seen it happen, not because it isn't real, but because you were never issued the right kind of eyes for the job. Night vision cameras exist specifically to do the job your retinas can't. That's most of what they're actually detecting. Layer that onto the brown dwarf and something clicks into place that didn't before. The object isn't some exotic outlier behaving in a way nothing else does. It's doing exactly what your hand is doing at a vastly larger scale, over a vastly longer time scale, left over from a birth that almost worked instead of a metabolism that's currently working. Heat leaking out in a wavelength that only certain instruments were ever built to catch. It took astronomers a genuinely long time to find the first confirmed one, and that's not a minor historical footnote. It's the whole difficulty compressed into one fact. Brown dwarfs were theorized decades before any were confirmed, because the theoretical case for them was solid, but the observational case was almost impossibly hard. Dim, cool, faint invisible light, easy to miss even when you were specifically looking. The first confirmed brown dwarf wasn't identified until 1995. Not the 1960s when the theory first appeared. Not the 1980s. 1995. An object type that had been predicted on paper for a generation before anyone actually caught one glowing quietly enough in exactly the wrong part of the spectrum, close enough to be measured. Since then, thousands have been found, mostly by infrared surveys built specifically to look for this kind of leftover warmth rather than ordinary starlight. Some estimates suggest brown dwarfs might be nearly as common as actual stars throughout the galaxy, which is a strange thing to absorb. An entire population of not quite stars, sitting out there in comparable numbers to the real thing, invisible to every telescope not specifically tuned to catch them, glowing the whole time in a colour the night sky was never going to show you no matter how carefully you looked. I don't know what to do with that fact except leave it where it is. Not every failure to see something means there's nothing there. Sometimes it just means you were looking with the wrong kind of eyes in the one direction they were never built to work. A star behind a curtain. It didn't choose. You'd think a star either shines or it doesn't. on or off, bright enough to see or too far to bother. That's the assumption most people carry around without ever examining it, and it holds up fine until you learn about the thing sitting in between the star and you that has absolutely nothing to do with the star at all. Space is not empty the way a vacuum jar is empty. Between stars, scattered thin but real, there's gas and dust, the leftover material from earlier generations of stars, blown outward by stellar winds and supernova explosions, drifting for millions of years before settling into loose clouds. Astronomers call this the interstellar medium, which is a dry name for something that turns out to matter enormously. A cloud like this can be so diffuse that by any everyday standard it's basically nothing, a handful of particles per cubic centimetre in the thinnest regions, and it can still, across enough distance, do something to a star's light that has nothing to do with the star's actual behaviour. The effect is called extinction, and the name is a little dramatic for what's actually a fairly mundane process. Dust grains, mostly carbon and silicate particles smaller than a wavelength of visible light, scatter and absorb the light passing through them. Blue light, with its shorter wavelength, scatters more easily than red. So light that passes through enough dust doesn't just get dimmer, it gets redder. The blue scattered away in all directions while the red pushes through relatively unbothered. This is, more or less, the same physics that makes a sunset red on Earth, just stretched out across interstellar distances instead of a few dozen kilometres of atmosphere. A star sitting behind a thick enough cloud of this material can be dimmed by a factor of 100, sometimes 1,000, without changing anything about its own output. The star itself is fine, burning exactly as it was going to burn, putting out exactly the light it was always going to put out. What changes is what happens to that light on the way here. Some of it scattered off course, absorbed into the dust and re-radiated at a different wavelength entirely, gone from the visible spectrum by the time anything reaches a telescope. This caused a genuine, sustained problem for astronomers for a long time, and it's worth sitting with how basic the confusion was. If you don't know a cloud of dust sits between you and a star, and the star looks dim, the obvious conclusion is that the star is far away, or intrinsically faint, or both. For decades, distance estimates to stars near the galactic centre were skewed by exactly this. Dust in the galaxy's disk absorbing and reddening the light so severely that stars appeared dimmer and therefore seemingly farther than they actually were. The correction wasn't trivial. It required mapping the dust itself, region by region, building a kind of extinction map for the galaxy, so that the dimming caused by dust could be mathematically subtracted from the dimming caused by actual distance. There's a particular kind of humility built into this correction, if you think about it long enough. Every distance ever calculated to a star obscured by dust carries, buried inside it, an estimate of how much a cloud of particles too small to see individually managed to interfere with a measurement made across trillions of kilometres. Get the dust estimate wrong and the whole distance is wrong, sometimes by a significant margin, and the star gets miscatalogued as something it isn't. The galactic centre itself is the extreme version of this problem. In visible light, you cannot see it at all. Not faintly, not at all. Somewhere between us and the core of the Milky Way sits enough accumulated dust and gas along the line of sight to block visible light almost completely, dimming it by a factor of roughly 1 trillion by the time it would reach Earth. The centre of our own galaxy, home to a supermassive black hole and a dense crowd of stars orbiting it at extraordinary speeds, is invisible to human eyes and always will be, no matter how good the telescope, because the obstruction isn't a limit of the instrument. It's dust sitting in the way, indifferent to the fact that it's hiding the middle of the galaxy we live in. What made the centre visible at all was switching wavelengths entirely, moving into infrared light, which passes through dust far more easily than visible light does, scattering less because its wavelength is longer than the dust grains causing the trouble. Infrared observations are how astronomers first tracked individual stars whipping around the galactic core at extraordinary speeds, eventually confirming the presence of the black hole sitting at the centre of all that motion. None of that came from seeing through the dust. It came from switching to a kind of light the dust mostly ignores. So the dimming was never a fact about the stars behind it. Not one of them. Every star that appeared faint, or reddened, or simply absent from a survey, was in most cases behaving exactly as expected, radiating exactly the light it should, and the story being told by its apparent brightness was really a story about the particular curtain of gas and dust that happened to be hanging in front of it that night, on that line of sight, for reasons that had nothing to do with the star and everything to do with the neighbourhood. The light happened to pass through on its way here. The star that bent around something else. Something is about to arrive that shouldn't be able to split into pieces, and yet it will, by the time it reaches the instrument waiting for it, and nothing about the star itself will have caused this. It left as one thing. It arrives as several. The difference happened entirely along the way, in the empty-looking space between. Gravity, in the everyday sense most people carry around, pulls on things with mass. Rocks, planets, people, apples that famously fall. It seems reasonable to assume light is exempt. Light has no mass, or close enough to none that the distinction barely matters. And for a long time that assumption held, right up until general relativity rewrote what gravity actually is. Gravity, in Einstein's description, isn't a force reaching out and grabbing things. It's the curvature of space itself, bent by the presence of mass, the way a heavy ball placed on a stretched sheet creates a dip that anything rolling nearby will follow. Light doesn't need mass to be affected by this. It just needs to travel through space, and if the space it's travelling through is curved, the light's path curves along with it. Not because something is pulling on it, because the space it's moving through isn't straight anymore. This was confirmed, famously, in 1919, when astronomers measured the position of stars near the Sun during a total solar eclipse, the only time the Sun's glare doesn't drown out nearby starlight, and found the stars' apparent positions had shifted, exactly as Einstein's equations predicted, because the Sun's mass had bent the space the starlight was passing through. It was one of the first real tests general relativity ever passed, and it passed cleanly, and it's easy to read that as a historical footnote rather than what it actually was. The first direct evidence that mass warps the very geometry that light has to travel through, whether light wants to or not. Widen the frame from a single sun to something with vastly more mass, an entire galaxy, or a cluster of thousands of galaxies bound together by gravity, and the same bending happens, just far more severely, because there's far more mass doing the bending. If a massive galaxy cluster happens to sit directly between Earth and a much more distant galaxy, the light from that distant galaxy doesn't travel in one straight line to reach us. It bends around the cluster's mass, following curved paths on multiple sides of it, like water flowing around a rock in a stream. And because those bent paths can reach Earth from several different directions at once, all curving around the same obstruction. A telescope pointed at that patch of sky doesn't see one galaxy. It sees the same galaxy's light arriving multiple times, from multiple slightly different angles, appearing as several distinct images scattered around the mass that bent it. Sometimes 2, sometimes 4. In the right alignment, stretched into a smeared near-complete circle called an Einstein ring, the light wrapping almost entirely around the intervening mass on its way past. None of this happened to the star or galaxy doing the emitting. It emitted its light the ordinary way in every direction, the way every luminous object does. The story of the bending, the splitting, the doubling and quadrupling belongs entirely to what sat between the source and the observer, to a stretch of space that had nothing to do with the star itself, except for happening to be in the way. Sit with that stretch of empty-looking space for a moment, because it's doing more work than it looks like it's doing. From where you're standing, the region between a distant galaxy and Earth looks like nothing. Vacuum, absence. And yet that supposedly empty region contains a galaxy cluster with a mass so enormous that light itself has no choice but to follow the shape that mass presses into the space around it. The way a heavy object placed in the middle of a stretched sheet forces anything crossing that sheet to follow its curve, whether or not the thing crossing has any weight of its own. There's a kind of quiet violence in that arrangement. Nothing struck, nothing broken, and still a path bent completely out of its original shape by something it never touched. Astronomers use this bending on purpose now, not just as a curiosity, but as a tool. The degree to which a distant galaxy's light gets bent and split depends on how much mass sits in the foreground doing the bending, which means the split images themselves can be measured to estimate how much mass is actually in that intervening cluster, including mass that emits no light at all and would otherwise be completely invisible. Some of the strongest evidence for dark matter, mass that doesn't shine, doesn't absorb, doesn't interact with light directly in any way that could be seen, comes from exactly this. Measuring how severely background galaxies get bent and split by foreground clusters, and finding the bending is far stronger than the visible mass in those clusters could account for on its own. The distortion in the light is, in these cases, the only signature of the missing mass. Nothing else gives it away. So the split image arriving at the telescope was never really about the galaxy that emitted it. That galaxy did nothing unusual, radiated its light in the ordinary way any galaxy does, indifferent to whatever sat along the route ahead of it. Everything strange about the picture, the doubling, the ring, the smeared arc, belongs to the geometry of the empty-looking space the light happened to pass through, and to the mass hiding inside that space, some of it visible, some of it not, all of it real enough to reach across millions of light years and reshape a beam of light that never asked to be bent, on its way to becoming an image that looks, by the time it arrives, like it came from somewhere it never actually was. Something too faint to argue with. For a long time, the honest answer to "is there anything there?" was simply, "we don't know," and the not knowing got treated in practice as a kind of no, not officially. Nobody wrote "does not exist" in a paper, but a signal too faint to separate from noise gets set aside quietly, and a thing set aside long enough starts to behave, in the collective memory of a field, like a thing that was never really there to begin with. This happened more than once, and it's worth sitting with how ordinary the mechanism was each time. A telescope has a noise floor, a baseline level of static, electronic jitter, stray light, cosmic ray hits on the detector, all the small unwanted signals that exist whether or not anything real is being observed. Anything fainter than that flaw is, from the instrument's point of view, indistinguishable from nothing at all. Not wrong, not disproven, just underneath the threshold where the equipment can tell the difference between very faint object and no object. Faint companion stars sat in exactly this gap for decades. A star bright enough to catalogue easily might have a much dimmer partner orbiting it, a small cool star or the pale spent core of an earlier one, sitting close enough in the sky that its glow gets lost in the brighter star's glare, the way a candle gets lost next to a spotlight. The orbit could sometimes be inferred indirectly, from a slight wobble in the brighter star's motion, a gravitational tug from something unseen. But inferring an object from its gravitational fingerprint and actually detecting its light are two very different kinds of knowing, and for a long time only the first one was available. I'll admit I find the Debris disk case the hardest one to hold steady in my head, maybe because it involves so much material behaving so quietly. Around many young stars, leftover gas and dust from the star's own formation settles into a flattened disk, the same kind of disk that, around our own sun, eventually built the planets. That disk glows, faintly, coolly, mostly in infrared, warmed just enough by the nearby star to radiate a weak signature of its own temperature. For decades, the technology to detect that signature reliably against the glare of the star it orbits simply didn't exist. The disks were there. They had to be there, if planet formation theory was right at all. Nobody could confirm it directly. The absence of a detection got, in the meantime, treated as evidence of absence, which it never actually was. The correction, when it came, wasn't dramatic. There was no single discovery that undid the mistake all at once. It came slowly, instrument generation by instrument generation, as detectors got more sensitive and techniques got better at subtracting the glare of a bright star to reveal whatever faint thing might be sitting close beside it. Coronagraphs that block the star's light directly, adaptive optics that correct for the blur introduced by Earth's atmosphere in real time, longer exposure times that let faint signals slowly accumulate above the noise floor, instead of getting lost in a single quick look. Somewhere in the last 3 or 4 decades, one debris disk after another, one faint companion after another, crossed over from theoretical to confirmed, and the correction, each time, was quiet. A paper, a footnote updating an old assumption. Nothing announced itself as a reversal. What sits oddly with me is how confidently the absence got treated, while it lasted, as if it were data rather than a gap in the data. Nobody set out to be wrong about this. The instruments genuinely couldn't see what wasn't yet visible to them, and reporting no detection was the honest and correct thing to report, given the equipment available at the time. But somewhere between not detected and probably not there, something slipped, some quiet upgrade in confidence that the observation didn't actually earn, and it slipped in more than one subfield, more than once, across a science that generally prides itself on being careful about exactly this kind of overreach. There's a specific unease in that pattern that I don't think fully resolves. It isn't that the scientists were careless. Most of them weren't, and said so, in careful hedged language buried in the discussion sections of old papers that nobody widely read. It's that hedged language has a way of getting lost by the time an idea filters out into textbooks, into casual understanding, into the sentence someone repeats second-hand without the qualifiers attached. No companion found becomes, a few retellings later, no companion, And the difference between those two claims is the entire history of instruments not yet being good enough. I keep coming back to the plainest version of the thought, which is also the least comfortable one. Absence of detection and absence of object are not the same claim, and treating them as interchangeable is one of the easiest mistakes available in any observational science, precisely because it doesn't feel like a mistake while you're making it. It feels like caution. It feels like sticking to the data. And most of the time, it probably is exactly that. But every faint companion later confirmed, every debris disk eventually imaged directly after decades of assumption that nothing was there, is a small, quiet reminder that the data never actually said nothing. The data only ever said not yet, not with what we have. A star that died before the light stopped coming. Somewhere inside a star right now, the core has started to run out of options, fusing lighter elements into heavier ones the way it has for millions of years, except each new fuel burns faster and buys less time than the one before it. Hydrogen giving way to helium, giving way eventually in the most massive stars to a final furious cascade of silicon burning into iron over the course of about a day, sometimes less, after eons of comparative calm. I've explained this one enough times that I've started noticing which part people actually flinch at, and it's never the part I expect. Iron is where the arithmetic turns against the star completely. Because fusing iron doesn't release energy, it costs energy, and a core that spent its entire existence generating outward pressure by fusing lighter things suddenly has nothing left to burn that will push back against its own weight. What happens next takes well under a second. The core collapses in on itself so fast and so completely that the outer layers of the star, still trying to fall inward in response, slam into the sudden, impossibly dense wall left behind and rebound outward in a shock wave that tears the rest of the star apart. A supernova, one of the most energetic events the universe is known to produce, briefly outshining the combined light of every other star in its galaxy, and it is, from beginning to end, unbelievably fast for something this large. Here's the part that doesn't fit together easily, and I don't think it ever fully will, no matter how many times you turn it over. The light from that event, whenever it happened, still has to cross the distance between the star and Earth before anyone here finds out. And for stars far enough away, that crossing takes longer, sometimes vastly longer, than the amount of time the star had left to live once its core started running low on fuel to burn. Take a supergiant a few thousand light years off, well within the range where this kind of thing gets discussed seriously by people who study stellar evolution. Say its core reaches the iron stage today, this evening, at this exact moment, and the whole collapse and rebound sequence plays out in under a second, the way it does. The light of that explosion sets off across the galaxy at the only speed light is capable of, and it will arrive at Earth in a few thousand years faithfully, carrying an accurate report of an event that finished happening almost instantly, almost as soon as it started. In the meantime, for every year of that multi-millennium gap, the star will appear in the sky exactly as it did the night before its core collapsed. Unremarkable, present. A point of light behaving like every other point of light nearby, radiating on, as far as anyone here could tell, business as usual. It's not that we're being lied to. Nothing dishonest is happening. The light reaching Earth tonight is telling the truth about the star as it existed at the moment that particular light left it, faithfully, precisely, the way light always does. It just so happens that as it existed then and as it exists now are two very different claims once distance and light speed get involved, and the gap between those two claims can be longer than the remaining life of the very star being described. Betelgeuse comes up in this conversation more than almost anything else, mostly because it's close enough, bright enough, and unstable enough to make the possibility feel immediate rather than abstract. It sits somewhere between about 500 and 700 light-years away. The distance is still argued over, which is itself a strange thing to have to admit about one of the most watched stars in the sky. And it is a red supergiant nearing what's generally understood to be the end stage of its life. It could go supernova within the next 100,000 years, which sounds like a long time until you remember that on stellar timescales, 100,000 years is close enough to any day now that astronomers genuinely discuss it as an open, live possibility, rather than something safely deferred to the far future. Here's where it slows down, because it deserves to, and because rushing through this part would do it a disservice. It is entirely possible, genuinely, not just poetically, that Betelgeuse has already exploded, that somewhere in the last 5 to 7 centuries its core reached the point of collapse, its outer layers were blown apart in a shock wave, and the star, in any meaningful physical sense, no longer exists in the form currently being described in astronomy textbooks. And there would be no way, none at all, for anyone on Earth to know this yet, because the only messenger capable of telling us, the light, is still somewhere between there and here, crossing a gap that takes centuries to close no matter how urgent the news being carried might be. Every night someone looks up at Orion's shoulder, they might be looking at a star that isn't there anymore, not there in a philosophical sense, not there in the most literal sense the word allows, gone, dispersed, its material already blown outward into the surrounding space, its identity as a single coherent object already finished. And the sky would give absolutely no indication of this, none, because it isn't hiding anything on purpose. It simply hasn't received the memo yet, and won't for as long as the light takes to arrive. I don't know how to sit with that without it changing something small about how you look at the sky afterward, and it's the kind of thing that resists coming to a tidy resting point. There's no way to check early, no shortcut, no signal that outruns the light itself to give advance warning, because nothing does. Light is the fastest messenger there is, and everything else about the event, the gravitational waves, the neutrino burst that would actually arrive slightly ahead of the visible light in a real supernova, still travels at speeds bound by the same universal limit. The information is coming, it is not here yet, and the star, whatever has already happened to it, whatever it currently is or currently isn't, will keep appearing exactly as it always has, right up until the night the light finally finishes its crossing and the sky, for the first time in centuries, tells the truth about something it has been quietly withholding the entire time, without meaning to, without any awareness that it was withholding anything at all. The colour that isn't the temperature. It looks like. Red means cool, blue means hot. Most people pick this up somewhere along the way and never really question it again, and it's not a bad rule, it's mostly true. It's just not the whole story, and the part it leaves out turns out to matter enormously once you're trying to measure something billions of light years away instead of just glancing at a stovetop. Start with why the rule works at all. Hotter objects radiate more of their energy at shorter wavelengths. This is basic thermal physics, True of a coil on a stove, true of a star. A cooler star, something around 3,000 degrees, glows reddish. A hotter one, north of 10,000 degrees, glows blue-white. It's called black body radiation, and it's reliable enough that astronomers use a star's colour as a genuine working estimate of its surface temperature. So far, so simple. Here's the interruption. A star's colour isn't only telling you about temperature, it's also being quietly altered by something that has nothing to do with heat at all. Motion. You already know this effect, even if nobody ever named it for you. Stand near a road. A siren approaches. The pitch is higher than it will be once the ambulance passes and starts moving away. Same siren, same actual frequency being produced the whole time, but the sound waves get compressed while the source is approaching and stretched out while it recedes. Your ear hears the compression as higher pitch, the stretching as lower. Nothing about the siren changed, only the distance between you and it changing in real time changed what reached your ear. Light does the same thing. Compress the wavelength, and light shifts toward blue. Stretch it, and light shifts toward red. A star moving toward Earth has its light compressed slightly, nudged bluer than it would otherwise appear. A star moving away has its light stretched, nudged redder. This is called Doppler shift, and it is not a small or exotic correction. It is one of the most heavily used tools in all of astronomy. So now you have two completely separate things capable of making a star look redder, it being cooler or it moving away from you, and two things capable of making it look bluer, being hotter or approaching. From a single glance at the colour alone, there is no way to tell which one you're looking at. This isn't a hypothetical confusion. It's a real problem astronomers have had to build entire methods around solving. The fix isn't guessing, it's spectroscopy, splitting a star's light into its full spectrum and looking at the exact positions of specific dark absorption lines, fingerprints left by particular elements like hydrogen or calcium, lines whose true, unshifted wavelengths are known with extraordinary precision from laboratory measurements here on Earth. If those lines show up shifted toward the red end of the spectrum compared to their known laboratory position, that shift is measuring motion, specifically, cleanly, separate from whatever the star's actual colour and temperature are doing. Compare the shift to the known temperature-colour relationship, and the two effects can be pulled apart. This is, more or less, the entire foundation of how astronomers learn the universe is expanding. In the 1920s, distant galaxies were found to have their light shifted toward the red end of the spectrum, and the amount of shift correlated with distance. The farther away a galaxy sat, the more red-shifted its light. What the edge of the disk is hiding. From far enough away, the sun looks like a flat, evenly lit coin, the same brightness from the centre, all the way out to the very edge, and that's the picture most people carry around without ever checking it against anything closer. Get closer. Not physically, nothing gets closer to the sun and reports back. But move the vantage point inward in imagination, the way you'd lean towards something to look harder at it, and the flat coin stops being flat. The edge of the visible disk, the part called the limb, is noticeably dimmer than the centre, not by a little. Under the right conditions, the edge can appear only a fraction as bright as the middle, and this isn't an illusion of contrast or a trick of the eye adjusting to glare. It's called limb darkening, and it's telling you something true and specific about the shape of a star that a flat disk of light could never tell you on its own. Here's what's actually happening, layered the way it actually sits, one depth at a time. The sun does not have a hard surface the way a rock does. What looks like its surface is really the photosphere, a layer a few hundred kilometers thick where the gas transitions from opaque to transparent enough for light to finally escape into space. Below the photosphere, it's hotter. Above it, cooler. And when you're looking straight at the center of the sun's disk, your line of sight travels almost directly inward, penetrating deeper into the photosphere before the light that reaches your eye gets emitted, catching photons from a hotter, deeper layer. Now shift your gaze toward the edge. The geometry changes without you doing anything different. This part is just trigonometry, unavoidable and exact. Looking toward the limb, your line of sight travels through the photosphere at a much shallower angle, almost grazing along it rather than boring straight down into it. That shallow path means the light reaching your eye from the limb is coming from a shorter distance into the layer, from gas sitting higher up, cooler, less luminous. Hotter gas glows brighter. Cooler gas glows dimmer. So the edge looks dimmer, not because there's less material there, but because your view of the edge is sampling a different depth than your view of the center, and that depth happens to be cooler. There's something almost bodily in how directly this maps onto vision itself, the way looking at any curved, glowing surface at a shallow angle changes what depth you're actually seeing into, whether that surface is a star or something as ordinary as a glowing coal viewed from the side rather than head-on. The angle changes the sample changes the colour and brightness. Nothing about the object itself needs to change at all. Layer that onto what you already know, and the flat coin stops being an approximation of the sun's surface and starts being a genuine record of the sun's temperature structure with depth, written in gradient rather than in numbers. The brightness falling off toward the edge isn't a flaw in observation, it's data arranged spatially saying, it gets cooler as you go up through this layer, and here is exactly how much cooler, encoded directly into how the light fades from center to rim. Astronomers use this gradient deliberately now, not just as an oddity to explain, but as a working tool. Measuring the precise shape of limb darkening across a star's disk gives a way to model the temperature structure of its outer atmosphere in detail that a single average brightness reading could never provide. The effect has also mattered enormously in exoplanet detection, because when a planet passes in front of a distant star and dims its light slightly, the exact shape of that dimming, how gradually it starts and ends, depends partly on limb darkening, and getting the limb darkening model wrong throws off the inferred size of the planet itself. The center was never brighter because it mattered more. It was brighter because your line of sight, at that particular angle, happened to reach in deeper before running out of opaque gas to hide behind, and that is the whole of it. Nothing more mysterious sitting underneath, though it took a fairly long time for anyone to work out that a gradient this quiet could be saying something this specific about the shape of a star nobody has ever touched, a star that flickers on a schedule. Nobody set. It is getting brighter right now, and it will keep getting brighter for a few more days, and then it will stop and reverse and get dimmer for a while, and then do the whole thing again, on a schedule so precise you could set a calendar by it. Some of them do, in fact. Astronomers have. I've watched the light curves of these stars plotted out more times than I can count, and there's still something in the regularity that catches me off guard, the way a heartbeat monitor catches you off guard even when nothing's wrong with it. The star in question is called a Cepheid variable, named after Delta Cephei, the first well-studied example, And what it's doing isn't erupting or dying or malfunctioning in any sense. It's breathing. Not metaphorically. This is close to the literal mechanism. The outer layers of certain stars, once they've evolved past a specific stage of their lives, become unstable in a very particular way. A layer of partially ionized helium sits just below the surface, and that layer is oddly good at trapping heat. As the star's internal pressure pushes the envelope outward, the star expands, cools slightly, and that helium layer becomes more transparent, letting trapped energy escape. The release of that energy causes the outer layers to fall back inward. As they compress, the helium reionizes, traps heat again, and the whole envelope gets pushed back out. Expand, release, contract, trap, over and over, at a rhythm set entirely by the star's own size and internal structure. This is called the Kappa mechanism, and it's less an event happening to the star than a property of the star's own architecture. The way a specific length of pipe organ will always resonate at the same note regardless of who's playing it. A star of a given mass, size and evolutionary stage will pulse at a period determined by those same physical properties. Change the mass or the size, and the period changes with it. This is where it stops being just a pretty phenomenon and starts being one of the more useful facts in the history of astronomy. In 1908, an astronomer named Henrietta Leavitt was cataloguing thousands of these variable stars in the Magellanic Clouds, small companion galaxies to the Milky Way, close enough together relative to their distance from Earth that every star in them could be treated as being at roughly the same distance from us. That detail mattered more than it sounds like it should. Because all the stars were at essentially the same distance, any difference in their apparent brightness had to come from a difference in their actual brightness, not from some being closer and others farther. And what Leavitt found, sorting through the data, was a relationship nobody had proven before. The longer a Cepheid's pulsation period, the brighter it actually was. Not roughly. Precisely enough to plot as a clean mathematical curve. That relationship is called the period luminosity relation, and once it existed, something remarkable, no, something strange, something genuinely useful, became possible. If you find a Cepheid anywhere in the universe and measure how long it takes to brighten and dim, you can read off, from Leavitt's curve, how bright that star actually is at its source. Compare that to how bright it looks from Earth, and the difference between the two tells you, through a fairly simple bit of physics involving the inverse square law, exactly how far away it is. A blinking star had become a ruler, not a metaphorical one, an actual, working, physically grounded method for measuring distances across the universe that no other technique of the era could reach. Edwin Hubble used exactly this method in the 1920s, finding Cepheid variables inside what was then called the Andromeda Nebula, and using their pulsation periods to calculate a distance so vast that the nebula could not possibly be part of the Milky Way at all. It was its own galaxy, an entire separate island of hundreds of billions of stars sitting roughly 2.5 million light-years away, discovered, or rather confirmed, since the debate had simmered for years, because a particular class of star happens to swell and shrink on a schedule tied directly to its own physical size. Here's the part that still gets me. Turning it over again after having explained it so many times, I should probably be used to it by now. The rhythm itself isn't random, isn't communicating anything, isn't even particularly dramatic if you were standing close enough to watch it happen in real time. Which you couldn't, but set that aside. It's just physics repeating itself, over and over, the same expansion and contraction playing out on a timescale of days or weeks depending on the star, driven by nothing more complicated than heat and opacity trading places back and forth inside a layer of gas a star didn't choose to have and can't really do anything about. And from that quiet, repetitive, almost mechanical breathing, an entire scale of the universe got built. Every galaxy distance calculated using Cepheids as reference points, every subsequent method calibrated against those Cepheid distances, all of it traces back to stars doing something that looks, from any reasonable distance, like nothing more than blinking. Slowly. On a schedule they never agreed to and have no way of breaking. The reversal of it is what sits with me longest, if I'm honest. It would be easy to expect that the most useful measuring tools in astronomy would come from something violent, something explosive, something that announces itself the way a supernova does. Instead, it came from stars simply doing the same quiet thing, again and again, patiently, for as long as they've existed. And the universe, it turns out, was willing to hand over its own scale to anyone patient enough to time the blinking. The star you can only hear about second-hand. Start with the star you can actually see. It's an ordinary one, blue-white, hot, orbiting something, and if you tracked its position carefully over months you'd notice it isn't moving in a straight line the way an isolated star should. It wobbles, traces out a small repeating loop against the background sky, the way a person walking a dog on a long leash traces loops around wherever the dog happens to be pulling, and the dog, in this case, cannot be seen at all. I've never been entirely comfortable with how much of modern astronomy comes down to exactly this, inferring the shape of something invisible from the way visible things move around it. And I don't think that discomfort is a flaw in the reasoning. I think it's just an honest response to how strange the reasoning actually is, once you sit with it instead of just accepting the conclusion. The visible star is being tugged. Something with real mass, real gravity is out there nearby, close enough to pull the visible star into an orbit around a shared centre of mass, and yet that something emits no light detectable by ordinary means. Two broad possibilities tend to explain this kind of arrangement. A neutron star, the impossibly dense leftover core of a star that already went supernova, or a black hole, the even more extreme outcome where the core's own gravity overwhelmed every force that might have stopped its collapse. Either way, whatever's out there orbiting alongside the visible star is, in the most direct sense, dark. Not dim, not faint, simply not emitting anything a telescope tuned to visible light could catch. So the case has to be built sideways, gathered from effects rather than from a direct look, one piece of circumstantial evidence layered against another. The wobble of the visible star is one piece, real, measurable, precise enough to calculate how much mass the invisible companion must have, based purely on how hard it's tugging. If that mass comes out well above roughly 3 solar masses, too much for a neutron star to hold itself together against its own gravity, the leading remaining explanation becomes a black hole, by elimination as much as by direct confirmation. The second piece of evidence tends to be more violent and stranger, and it's the one that actually first cracked this problem open. If the invisible companion sits close enough to its visible neighbour, its gravity can pull material directly off the outer atmosphere of the visible star, actual gas, actual mass, siphoned away and pulled into orbit around the unseen object. That gas doesn't fall in cleanly. It spirals, forming what's called an accretion disk, and as it spirals inward, friction and gravitational compression heat it to extraordinary temperatures, millions of degrees in the innermost regions, hot enough that the disk radiates strongly not in visible light but in X-rays. Cygnus X1 was the first strong case built this way, back in the 1960s and 70s, a bright, ordinary blue supergiant orbiting something unseen, with X-rays pouring out of the space between them, exactly the signature you'd expect from material being torn off the visible star and dragged screaming into an accretion disk around something with no surface at all to land on. It took years of careful argument. There was a real, serious scientific bet placed over whether it actually was a black hole, one that got conceded decades later, before the case was considered settled enough to teach without qualification. Even now, saying it plainly still requires a small mental adjustment. The object at the centre of all that X-ray light has never been seen. Not once. Everything known about it, its mass, its presence, its effect on everything nearby, comes from watching what it does to its neighbour, never from looking at it directly. There's something almost bodily in how this detection actually works, if you let yourself sit with the mechanics of it rather than the abstraction. A star being slowly stripped of its own outer layers by something it's tethered to and can't escape. Material pulled away in a continuous stream, heated to a scream of X-rays on its way into a darkness with no bottom. The visible star isn't just a passive marker whose wobble happens to be useful. It's being actively fed upon, in the most literal gravitational sense that phrase can carry, and the evidence of the invisible object's existence is written directly into the wound. I don't think there's a clean way to end this one, and maybe that's honest, given how much of it is still built on inference rather than a direct look. Every black hole discovered this way, and there are dozens now, catalogued across the galaxy, with more added as X-ray surveys get better, was found the same way this first one was. Not by seeing it, but by watching something else nearby behave as though it were being pulled by something that isn't there, and being pulled apart by it besides. The object itself stays exactly where it's always been. Absolutely silent, entirely dark, known only through what it's doing to the one thing close enough to complain. A beam that only exists if you're standing in the right spot. Somewhere, right at this moment, a star is about to die in a way that briefly outshines an entire galaxy. Not metaphorically, actually outshines it, for a handful of seconds, before fading almost as fast as it flared. And whether anyone on Earth ever finds out depends on something that has nothing to do with the explosion itself. These events are called gamma-ray bursts, and they're the most energetic explosions known to happen anywhere in the universe since its earliest moments. Most seem to come from the collapse of a massive, rapidly spinning star directly into a black hole, or from the violent merger of two neutron stars smashing together. Either way, the result is a brief, catastrophic release of energy so extreme that early estimates of their power, taken at face value, implied something almost impossible. An amount of energy that would have required converting a significant fraction of a star's entire mass directly into gamma radiation in a matter of seconds. That estimate turned out to be wrong, not because the explosion was smaller than it looked, because it wasn't shining in every direction at once. Zoom in on the mechanism past the explosion itself, down to what's actually happening at the core of the collapse. When a massive star's core collapses into a black hole, the surrounding material doesn't fall in uniformly. Some of it, along the rotational axis, gets funneled and accelerated into two narrow jets, blasting outward at velocities extremely close to the speed of light, squeezed into a beam only a few degrees wide. A tight column of energy, not a sphere of light expanding evenly in all directions the way a supernova's glow does. This changes everything about how bright the event appears to be, depending entirely on where you happen to be standing. If Earth sits directly in the path of one of those narrow jets, the burst looks almost unbelievably powerful, briefly the brightest thing in the observable universe, detectable across billions of light years. If Earth sits even a few degrees outside that beam, the same explosion, the same physical event, the same star, the same collapse, would produce nothing detectable at all. No burst, no signal, nothing to record because the beam simply never crossed our position in the sky. Here's where it needs to slow down because the implication is larger than it first sounds. Every gamma-ray burst ever recorded was recorded specifically because Earth happened to be sitting inside its narrow beam. This means, almost certainly, that we're only catching a small fraction of these events actually occurring throughout the universe. The ones where the geometry lined up, where the beam swept across exactly the right patch of sky. Every burst that fired in a direction even slightly away from us happened in complete silence, as far as any instrument on Earth is concerned, indifferent to whether anyone was watching or capable of watching. Once astronomers understood the beaming, the true energy output of these events had to be recalculated entirely. The number initially assumed, treating the explosion as if it radiated equally in all directions, was called the isotropic equivalent energy, and for the brightest bursts it implied genuinely impossible values. Correcting for the beam's actual narrow width brought the true energy down to something merely extraordinary, rather than physically absurd, still more energy released in seconds than the sun will produce across its entire multi-billion-year lifetime, but no longer requiring physics nobody could explain. Confirming the beam's width at all took its own kind of detective work. As the burst fades, its afterglow, the lingering glow in X-ray, optical, and radio wavelengths as the jet slows and spreads while colliding with surrounding gas, shows a distinctive break in its brightness decline at a specific point, a moment where the light starts fading faster than the physics of a simple, spherical explosion would predict. That break happens when the jet, still moving close to light speed, has spread and slowed enough that its edges become visible to the observer for the first time, effectively revealing the boundary of the beam from the outside. Measuring exactly when that break occurs lets astronomers calculate how narrow the original beam actually was. So the brightness recorded on Earth for any of these events was never really a property of the explosion in some absolute sense. It was a property of geometry and luck, and the accident of standing in the one narrow column out of an entire sphere where the light happened to be aimed. Move a few degrees, and the same star dying the same catastrophic death would have gone entirely unnoticed, its light aimed at nothing, its brightness meaningless to anyone it never reached. The star that was never one star. Point an ordinary backyard telescope at a fairly bright, unremarkable-looking star, and sometimes, if you're patient and the seeing is good that night, something happens that a casual glance would never catch. The single point of light softens, spreads slightly, and then resolves into 2 points, sitting close together, distinct. Not one star. 2. There the whole time, doing this the whole time, and nobody in that spot on Earth knew it until the resolution improved enough to catch them separately. This is more common than it sounds like it should be. A significant fraction of the stars in the sky, estimates run somewhere around half, maybe more depending on the stellar population being studied, aren't single stars at all. They're binary systems, two stars gravitationally bound, orbiting a shared centre of mass, sometimes separated by a distance you could resolve with a decent amateur telescope, sometimes separated by so little that no instrument built so far can tell them apart directly. And the only evidence of the second star comes from indirect signatures, folded into the light of what looks, at every casual glance, like one ordinary point. Widen the frame slightly, out past individual binaries, and the situation compounds. Some systems aren't pairs at all, but small crowds. 3 stars, 4, occasionally more, all bound together in orbits nested inside each other, close enough at a distance to blur into what any pre-modern observer would have confidently logged as a single star with a single set of properties. Brightness, colour, position. All of it an average, a blend, standing in for what was actually several distinct objects standing close enough together to fool the eye and, for a long time, fool the instruments too. This caused real documented confusion in the earlier star catalogues. A star logged as unusually bright for its apparent colour, or with a spectrum that seemed to contain contradictory signatures, features that looked like they belonged to 2 different types of star layered on top of each other, sat as an unsolved oddity in some cases for decades, until better resolution or better spectroscopy revealed the actual explanation. It was never one star behaving strangely. It was 2 or 3 stars of genuinely different types, standing close enough together along the same line of sight that their combined light had been misread as the signature of a single, peculiar object. Algol is one of the oldest known cases of this kind of blended identity, and one of the strangest histories attached to it. Ancient observers noticed it dimmed periodically on a fairly regular schedule, and the star picked up a folkloric reputation tied to that flickering long before anyone had a physical explanation. The actual cause, worked out much later, is a close binary. 2 stars orbiting each other tightly enough that from Earth's vantage point, one periodically passes directly in front of the other, blocking part of its light in a predictable repeating eclipse. What looked, for most of human history, like a single unstable star turned out to be a strictly geometric consequence of 2 ordinary stars taking turns hiding behind each other on a schedule set by nothing more mysterious than orbital mechanics. Modern instruments have pushed this further than a casual look ever could. Spectroscopic binary detection doesn't rely on visually resolving 2 separate points of light at all. It works by splitting a star's combined light into a spectrum and watching for absorption lines that shift back and forth periodically, each set of lines tracing the orbital motion of one component pulling toward and away from Earth in turn. Some binaries discovered this way have never been visually separated by any telescope, not because the technology has failed, but because the 2 stars genuinely sit too close together, physically, for any optical instrument to distinguish them as separate points no matter how good the resolution gets. The only evidence they're 2 stars rather than one lives entirely in the wobbling pattern of their combined spectral lines. Sit with what that actually means for a moment, layered under everything else already said about these systems. Some of the stars in every catalogue, catalogued with a single set of coordinates, a single brightness, a single spectral classification, are not describing one object. They're describing an average, a blended reading standing in for 2 or more actual stars that have simply never been far enough apart from Earth's specific vantage point for anything human-built to separate them. The catalogue entry is honest about what the instrument could measure. It just was never able to say the one thing that mattered most. How many things were actually being measured at once? There's a particular kind of vertigo folded into that, similar in shape to some of what came earlier in this chapter's own genealogy of surprises, though I won't dwell on the resemblance. A point of light that seems perfectly ordinary, perfectly singular, sitting exactly where a star is supposed to sit, doing exactly what a star is supposed to do. And it might not be one thing at all. It might be a small crowd, standing close enough together to hold hands across the vast dark between them and appear, from far enough away, indistinguishable from something solitary. Every improvement in resolution, every generation of better instruments, keeps splitting apart objects that used to be counted as singular. Nobody knows with certainty how many of the stars currently logged as single points in modern catalogues will eventually turn out, under some future instrument not yet built, to be 2 or 3, standing close enough together that even today's best technology still reads them as 1. What changes when you know the delay? Everything already said has just finished happening, in the sense that it's all still sitting in the room, layered on top of itself the way sediment settles, one idea resting quietly on the one before it without erasing it. The neutrinos are still going through you. The light from the core of the sun is still this second taking its slow blind walk outward through plasma that has no interest in letting it leave. Somewhere, a beam from a dead star's magnetic pole is still sweeping past a point in space that may or may not include Earth. None of that stopped while the rest of this was being said. It was all happening at once, the whole time, underneath everything. Here's the fact that reorganizes all of it, and it deserves to be said plainly without dressing it up. None of these stars were ever lying. Not one. The delay wasn't deception. The beaming wasn't a trick. The blend of 2 stars pretending to be 1 wasn't dishonesty on the part of the light. Every strange, disorienting, faintly upsetting thing described across everything that came before, this was simply light, doing exactly what light does, under the actual physical conditions of the specific patch of universe it happened to be crossing. Sit with that slowly, because it's the kind of correction that changes the shape of everything it's placed under, retroactively, without needing to add anything new. The star that might already be dead wasn't withholding that fact out of some strange stellar reticence. It was obeying a speed limit that applies to all information everywhere, the same limit that governs a neutrino leaving the sun's core, and a photon escaping a supernova, and a radio signal completing an eclipse of 2 stars taking turns in front of each other on a schedule set by pure orbital mechanics. The beam that missed Earth by 5 degrees wasn't hiding. It was simply aimed somewhere else, the way every beam of anything is aimed somewhere specific and not everywhere at once. The blended light of 2 stars mistaken for 1 wasn't a deception laid by the stars themselves. It was geometry and distance, and the plain fact that 2 points close enough together will always look, from far enough away, like a single point, until the observer gets close enough or clever enough to tell otherwise. What was actually wrong, the entire time sitting underneath every single chapter, without ever being named directly until now, was a quiet, reasonable, almost invisible assumption that light arrives simply, that looking is the same as knowing, that a point in the sky, glowing steadily, is reporting on itself accurately, immediately, honestly, the moment you happen to look up. It never was, not once. Every photon reaching an eye or an instrument has already survived a specific, particular journey, through a core that took tens of thousands of years to let it go, or past a cloud of dust that stole 3/4 of its brightness before letting the rest through, or around the mass of an entire galaxy cluster that bent it into 2 or 4 separate paths, or across a gap of centuries or millennia during which the thing that made it may have already stopped existing in the form that made it. The light doesn't carry a warning label explaining which of these things happened to it along the way. It just arrives, uniform, indistinguishable at a glance from any other light, carrying its actual history invisibly, folded into wavelength and timing and geometry that only patient measurement can unfold again. There's something almost bodily in how slowly this settles once you let it. You'd think a fact like this would announce itself, change how a person feels standing under a clear sky, immediately and dramatically. It mostly doesn't. Most nights will go on looking exactly the way they always have. Ordinary, quiet ceiling of small steady lights doing nothing unusual. The change isn't in what the sky shows you. The change is in what you now know is folded into that showing, invisible, unannounced, sitting there the entire time whether or not anyone bothers to remember it. The stars were never misbehaving. Not the one whose light took a detour around a galaxy cluster. Not the one that might already be gone. Not the one that turned out to be 2 stars holding a very old, very quiet secret about how close 2 things can stand together and still be mistaken from far enough away for one. Every single one of them did exactly what physics required, under the actual conditions of the specific stretch of universe their light happened to cross. The only thing that was ever wrong this whole time was the assumption that arrival meant honesty. That distance was free. That looking up and seeing something meant the something being seen was still there, unchanged, waiting, the way it appeared to be waiting the whole time you weren't looking. It wasn't waiting. It was just far away, and the light took exactly as long as it was always going to take, and said, in the end, exactly and only what had actually happened, however long ago that turned out to be,